Welcome to the Curious Voyager. It's lovely to have you here. Wherever you are tonight, whatever corner of the world has gone quiet around you. Maybe there's a lamp still on somewhere across the room, throwing a soft circle of light onto the ceiling. Maybe the blanket is pulled up just so. Maybe you've found the exact warm spot where the pillow gives way under your head and your shoulders finally let go of the day. Wherever you are, however you've arranged yourself for the next little while, I'm glad you came. And before we drift off into the strangest, gentlest story I know how to tell, let me ask you the question I always like to ask. Where in the world are you watching from tonight? What time is it in your particular corner of the dark? Some of you are listening in the deep middle of the night, the kind of hour where the house ticks and settles and the rest of the street is asleep. Some of you are far away from me in a time zone I'll never see, with the morning still hours off. It comforts me to think of all of you out there, scattered across the planet, each in your own pool of quiet, all listening to the same calm voice. If you'd like to, leave a little note and tell me where you are. I read them and they're lovely. And if you find you enjoy these slow journeys, if you'd like more nights like this one, a gentle like and a subscribe really does help this sleepy little channel keep going. Small creators like me rely on it more than you'd think. And to those of you who've already subscribed, who come back night after night and let me sit on the edge of your bed and ramble about the universe until you drift off, thank you, truly. You're the reason this exists. Now, let me make you a promise, and let me make you a second promise right after it. The first promise is about pace. We are going to take this slowly tonight. So slowly. There is nowhere to be, nothing to finish, no test. At the end, I am going to walk you through 5 experiments, real ones, with real names and real dates attached. And I'm going to take my time with every single one of them. If your eyes close before we reach the end, that's perfectly fine. That's the whole point, really. The ideas will still be here in the morning. The universe isn't going anywhere. You don't have to hold on to any of this. You don't have to understand every piece of it. Let it wash over you the way you'd let warm water wash over you. And if a thought slips away before you can catch it, just let it go. There's no need to grasp every equation. There's no need to grasp any equation, honestly. I'll do the carrying, you just rest. And the second promise, the one I have to confess to, is this. I'll try not to make this so interesting that it keeps you awake. I really will try. But the things I'm about to tell you are genuinely some of the most beautiful and unsettling discoveries human beings have ever made. And there's a small risk that one of them lodges in your mind and won't let go. If that happens, I'm sorry. But at least you'll have learned something true while you were lying there. A fair trade, I think. So settle in, pull the blanket a little higher, let your breathing slow down to match the pace of my voice, and let me tell you about a film, a real piece of film recorded by real people that I think about more than almost anything else I know. Picture a laboratory. It's the year 1989. The place is a research facility belonging to Hitachi in Japan, and a physicist named Akira Tonomura and his team are about to record something that, when you really sit with it, quietly takes the floor out from under everything your senses have ever told you about the world. They have a machine, and this machine can do something almost unbelievably delicate. It can fire a single electron, just one of the tiniest pieces of matter there is. One of the little specks of charge that swarm inside every atom in your body, in the blanket over you, in the air you're breathing right now. They can release them one at a time, like dropping single grains of sand, one, and then a long pause and then another, across an empty chamber toward a screen that lights up wherever an electron lands. And here is the setup that matters. Between the electron and the screen, there's a barrier with 2 narrow openings in it, 2 slits, 2 little doors side by side, and nothing else for the electron to pass through. So you'd think, anybody would think, that each electron has to go through one door or the other. It's one tiny particle. It can't go through both. It goes through the left one or it goes through the right one, and it lands on the screen somewhere behind whichever door it chose. Send a few thousand of them through one at a time, and you'd expect two simple smudges to build up on the screen, two clumps of light, one behind each slit. That's what a stream of little pellets would do. That's what your intuition, the part of you built to catch falling cups and dodge rain, absolutely insists must happen. Now watch the film. The first electron goes through and it lands as a single dot, a pinprick of light exactly where you'd expect a tiny particle to land. One dot. So far, so sensible. A second electron, a second dot, somewhere else on the screen, seemingly at random, a third, a fourth. For a while it looks like nothing at all, just a scatter of lonely points sprinkled across the screen, like the first few drops of rain on dry pavement. No pattern to them, no order, just dots appearing one by one wherever each electron happened to go. But keep watching, let the dots accumulate, hundreds of them now, then thousands, and out of that random-looking sprinkle, slowly, the way a photograph used to swim up out of nothing in a darkroom tray, a pattern begins to form. Not two clumps, not the two smudges your intuition promised. Instead, bands, stripes, bright vertical bands of light where electrons land in great numbers, separated by dark bands where, strangely, almost no electron ever lands at all. Bright, dark, bright, dark, bright, marching across the screen in an even rippling pattern. That pattern has a name. It's called an interference pattern, and it is the unmistakable signature of a wave. Now stay with me here, because this is where the flaw goes. We weren't sending waves, we were sending single electrons, one at a time, each one alone in the chamber, each one landing as a single solid dot. There was never more than one electron in there at a moment. Each one was fired, traveled, and landed before the next one was even released. So whatever made those bands, whatever piled the electrons up into bright stripes and forbade them from the dark ones, it cannot be a crowd of electrons jostling against each other. Each electron was alone. Each electron made its single dot in isolation. And yet somehow, where each individual lonely electron is allowed to land is governed by a wave-like pattern, as if each single, solid, isolated particle passing through that barrier was somehow aware of both doors, as if it explored both paths at once, both possibilities at once, and the two possibilities folded together, interfered, and that folding together is what decided where the dot was permitted to appear and where it was absolutely forbidden. A single particle interfering with itself, with the path it took and the path it didn't. I want you to let that just sit in the room with you for a moment, the way you'd let a strange and lovely piece of music finish ringing before you say anything. We have the film of it. It is not a thought experiment, not a metaphor, not a trick of mathematics. Tonomura's team at Hitachi recorded the dots arriving one by one and the pattern building up out of them. In 1989, you can watch it. It happened. And it wasn't the first time either. This experiment has a long and patient history. Long before that film, back in 1961, a physicist named Klaus Jönsson, working in Tübingen in Germany, had already sent electrons through a double slit and seen the interference bands appear. People had wondered for decades whether you could ever do it cleanly with electrons, and Jönsson showed that you could. So by the time Tonomura's camera caught the dots arriving one at a time, the result itself was already old news to physicists. What the film added was the thing the rest of us needed to truly feel it, the visible, undeniable spectacle of single particles alone building a wave. And there's a piece of arithmetic underneath all this that I find quietly reassuring, so let me give it to you gently. Those bands aren't randomly spaced. The distance between one bright stripe and the next can be calculated in advance before you ever run the experiment from a simple little relationship. Every particle, it turns out, has a kind of wavelength associated with it. It's called the de Broglie wavelength, after the French physicist who first proposed it. And it's given by a tidy formula. The wavelength equals a fixed number of nature, called Planck's constant, divided by the particle's momentum. Lambda equals h over p, if you ever see it written down. You don't need to do anything with that. I only mention it because of what it means. It means that the spacing of those mysterious bands isn't mystical at all. It's predictable. You can work out exactly how far apart the stripes should be, and when you run the experiment, the stripes land exactly there, matched to the prediction, to within the precision of your measuring tools. The strangeness is real, but it isn't sloppy. It's lawful. There are rules. They're just not the rules you expected. And here's a detail I love about those dark bands, the empty stripes, where no electron ever lands. Think about what that actually means. There are places on that screen where, if you opened just one of the two slits, electrons would happily land, plenty of them. But open both slits and suddenly those same spots become forbidden, off limits. By adding a second door, a second way for the electron to get through, you make certain destinations impossible that were perfectly possible before. Giving the electron more paths to travel takes away places it's allowed to arrive. The dark bands are the places where the two possibilities, the through the left and the through the right, cancel each other out so completely that the electron is forbidden from landing there at all. A single particle interfering with the set of paths it could have taken, but didn't. I find that almost unbearably strange, and I've thought about it for years. And before you let yourself drift on the thought that maybe this is just a quirk of electrons, just some peculiarity of tiny lonely things, it isn't. Not at all. The same pattern has been shown with photons, with particles of light, with neutrons, with whole atoms, and then most astonishingly with molecules, big ones. In 2019, a group in Vienna, Fine and his colleagues, sent molecules made of around 2,000 atoms through this kind of apparatus, great lumbering things by the standards of the quantum world, with a mass of something like 25,000 atomic units, and they still interfered. They still built up the bands. So this is not a loophole that only opens for the smallest specks of nature. It reaches up, at least a little way, into the world of things almost large enough to imagine. The wave is not a property of being tiny, it seems to be a property of being. So you're lying there, and the picture so far is genuinely beautiful and genuinely unsettling. A single particle behaves as though it goes through both doors and folds together with itself. Fine. We can almost make peace with that, the way you can make peace with a strange dream while you're still inside it. But here's where the story turns, and here's where almost everyone who tells it gets the next part wrong. Because there's an obvious question to ask, isn't there? If the electron seems to go through both slits, well, let's just look. Let's put a little detector at the slits, some device that can tell us which door each electron actually went through. Left or right, we'll catch it in the act, we'll find out the truth. So physicists did exactly that. They placed a which path detector at the slits, an instrument capable of recording for each electron which opening it passed through, and they ran the experiment again, and the interference pattern vanished, gone. The bands disappeared entirely, and in their place came the two simple clumps your intuition wanted all along. Two ordinary smudges, one behind each slit, exactly as if the electrons were just little pellets, choosing one door or the other. The moment you set up a way to know which path each electron took, the wave-like behavior collapsed into the boring, sensible, particle-like behavior. Look, and you get two clumps. Don't look, and you get the rippling bands. Now, this is the exact moment where the popular story goes off the rails, and I want to gently steer us back onto the track, because the truth here is so much more interesting than the myth, and so much more calming too. The myth the version you've heard 100 times, the version that gets repeated in breathless videos and dinner party conversations. The myth says that the particle knows it's being watched. That consciousness, the human mind, the act of a person looking, is what reaches out and changes reality. That the universe behaves one way when no one's observing and another way the instant a mind pays attention. It's a seductive idea. It makes us feel central, important, woven into the fabric of things, and it is, as far as we can tell, simply not what's happening. Here's the true version. Let me lay it down softly. The pattern doesn't vanish because a conscious mind looked. It vanishes because of something called decoherence, and decoherence is, at heart, about information, not about minds at all. Think of it this way. When you place that detector at the slit, the detector has to interact with the electron in order to register which way it went. It has to become physically linked to it, tangled up with it. Physicists use the word entangled. The detector and the electron are now bound together so that the state of one is tied to the state of the other. And once that happens, the information about which path the electron took has leaked out into the wider world. It's recorded, it exists. It's spread into the environment and into the particles of the detector, and then potentially into everything those particles touch. And here is the crucial part, the part that makes all the difference, and that the myth completely misses. No one has to read the detector. No human being ever has to look at it. No mind has to become aware of anything at all. The mere fact that the which path information now exists in principle, recorded somewhere in the physical world, even if every scientist went home and the lab sat empty all night. That is enough to destroy the interference. The wave-like folding together of the two possibilities only survives as long as the two possibilities remain truly indistinguishable, as long as there is, in principle, no way to tell which path was taken. The instant the universe itself contains the answer to which door, the soft overlap of possibilities hardens into a single definite fact, and the bands disappear. This idea, that the spreading of information into the environment is what turns quantum fuzziness into the solid, definite world we know, was worked out by a physicist named Zeh, who published the core idea back in 1970, and it was developed and deepened in the years afterward, especially by Wojciech Zurek. Decoherence, the leaking of which path information into the wider world. It is one of the most important and least celebrated ideas in all of physics because it quietly dissolves so much of the mysticism that's grown up around the quantum world. It tells us that you, your eyes, your mind, your attention, none of it is required. The world doesn't wait for you to look. It decoheres on its own, constantly, everywhere, because everything is always interacting with everything else, always trading information, always becoming entangled in vast, uncountable ways. That's why your bedroom looks solid and definite and ordinary. Not because you're watching it, because it watches itself in a sense, because information about where everything is leaks endlessly into the air and the light and the walls, so thoroughly and so fast that the soft quantum overlaps never get a chance to show themselves at the scale of a coffee cup or a hand or a sleeping body. The reason the double slit reveals the strangeness at all is that physicists work so hard to keep that information from leaking. They isolate the electron. They keep the chamber empty and quiet and undisturbed, so that as the electron travels, nothing learns which way it went. They protect the indistinguishability. And only inside that carefully guarded silence does the wave get to show itself. The moment any record form, and any record at all, anywhere, the silence breaks and the ordinary world snaps back into place. So the lesson of that vanishing pattern is not the universe cares whether you're paying attention. The lesson is gentler and stranger, and I think more profound. The lesson is that what determines reality is information, what can, in principle, be known. Not what is known by some mind, but what is knowable at all, what the universe itself has on record. That's the load-bearing thing. Hold on to that one idea if you hold on to anything tonight, because it's the thread that runs through every experiment I'm going to tell you about. Not minds, information. And physicists have gotten so good at this that they can now watch single electrons in real time, controlling which slit is open, switching from a single slit to a double slit and back, detecting each electron as it arrives. In 2013, a group, Bach and his colleagues, built an apparatus that let them open and close the individual slits at will and detect the electrons one at a time as the pattern formed, with the kind of control the early pioneers could only dream of. So this isn't fragile, half-glimpsed lab folklore. It's robust, repeatable, controllable, filmed, refined across more than half a century, from Jönsson in Tübingen in 1961 to Tonomura's beautiful film in 1989 to Bach's exquisite real-time control in 2013. The result holds. The world really is like this. Now let your mind go soft for a moment and just rest on where we've arrived. We started with what seemed like an unbreakable rule of common sense. A single thing goes through a single door. And we found that nature simply doesn't honor that rule when no one and nothing can tell which door was used. And we found that the thing that restores ordinary behavior isn't a watching mind, but the mere existence of a record, information, leaking into the world. Which leaves a question hanging in the dark above your bed, a question I want you to drift toward rather than chase. If it's information that matters, if the bands vanish because a witch path record comes into existence, then what happens if you erase that record? What if you let the detector capture the witch path information so the interference is destroyed, but then afterwards somehow you reach in and wipe the information away again so that it no longer exists, so that nothing in the universe can tell which door was used? Could you bring the wave back? Could you, after the fact, after the electron has already done whatever it did, restore the interference simply by deleting the knowledge? It sounds impossible. It sounds like cheating time itself. And the strangest thing of all is that physicists have actually tried it. They built the experiment. They reached in and erased the information after the particle had already arrived. And what they found is so often described so badly and so beautifully as changing the past. But that, like the watching mind, is a myth. The truth is quieter and cleaner and somehow even stranger. And it's where we'll go next, slowly, in just a little while. For now, there's nothing you need to do. Let the dots keep arriving on that screen behind your closed eyes, one by one, building their patient pattern out of the dark, and let yourself sink a little deeper into the warmth, because the universe has been keeping these secrets for a very long time, and it will keep them just as well while you rest. Let me settle back then before we follow that thread and sit for a moment with where we already are, because something happened a few minutes ago that deserves to be marked, even if your eyes are closed and your breathing has already started to slow. Let me tell you about the film itself, the actual film. In 1989, Akira Tonomura and his team at Hitachi did something that almost no one had managed before. They sent electrons one at a time across a chamber, and they caught each one as it arrived. Not a beam, not a flood. Single electrons fired so far apart in time that there could never be two of them in flight at once. Each one on its own, alone in the dark, with nothing else to interfere with. And they recorded where each one landed. At first, the screen looks like nothing. A dot here, a dot there, a dot somewhere off to the side, scattered, random, meaningless, like the first few drops of rain on dry pavement before the storm decides where it wants to fall. If you saw only the first dozen electrons, you would swear there was no pattern at all. Just specks. Just noise. But they let it run. hundreds of electrons, then thousands. And slowly, the way a photograph used to rise out of the chemical bath in a dark room, a shape began to emerge from all those separate, lonely dots. Bands, stripes, bright lines where electrons love to land, and dark lines where somehow they refused to. An interference pattern, the exact signature of a wave, passing through two openings and overlapping with itself on the far side. And here is the part I want you to hold gently without working too hard at it. Each electron arrived as a single point, one dot, a particle, undeniably, leaving its single, small mark. No electron ever smeared itself across the screen like a wave. They came one at a time, each a clean little period at the end of a sentence. And yet the pattern they built, all of them together, was a waves pattern, as if each single electron traveling alone had somehow gone through both slits, interfered with the paths it did not take, and only then chosen a single place to land, a place allowed by that interference and no other. A single particle interfering with itself. With the journeys it didn't make, the dark bands are the strangest part of all. Those are the places where the electron is forbidden to land, not unlikely, forbidden. There are spots on that screen where if the electron was simply a tiny ball rattling through one door or the other, it absolutely could go, and yet it never does, never. The two sets of possibilities, the path through the left slit and the path through the right, cancel each other there, the way two ripples meeting crest to trough flatten the water to perfect stillness. And so the electron, which is one thing, somehow obeys a rule written by two things and avoids the forbidden ground. This isn't a metaphor I'm reaching for. The spacing of those bright and dark bands can be calculated in advance with a small piece of arithmetic. There's a quantity called the de Broglie wavelength. Every particle has one. And it's simply Planck's constant divided by the particle's momentum. L equals h over p. You don't need to remember that. Let it slide right past you. The point is only this. You put in the electron speed and mass, you turn the little crank of the equation, and out comes a number, how far apart the bands should sit. And then you go and look at the real screen, the real dots, the real stripes, and they match to within the precision of the measurement itself. They match. The wave that has no business being there is somehow exactly the right size. So this is real, this is filmed, this is arithmetic, confirmed by photographic plates. Whatever is happening, it is not a trick of fuzzy thinking or a story scientists tell to sound mysterious. It is one of the most carefully verified facts in all of physics. Hold on to that softly as we take the next slow step, because the next step is where the trouble starts, the good kind of trouble, the kind worth losing a little sleep over, though I'd rather you didn't. Long before Tonomura's film back in 1961, a young physicist named Klaus Jönsson working in Tübingen had already pushed electrons through a double slit and seen the fringes appear. So the effect itself was decades old by the time we had the movie of it. People had been living with this strangeness, turning it over for a long time, and someone, inevitably, asked the obvious question, the question you might be forming right now, half asleep at the edge of the dark. If each electron only lands in one place, one dot, then surely it went through one slit, left or right. Not both. So why don't we just look? Why not put a little detector at each opening? A tiny sentry that notices when an electron passes, and simply watch which door each one uses. And then we'd know. We'd catch the particle in the act of being a particle, and the mystery would dissolve. So they did exactly that. They placed a which path detector at the slits, something capable of recording which way each electron went, and the interference pattern died, just like that. The moment you can tell which slit the electron used, the bands vanish, the bright stripes and the forbidden dark ones smooth away, and in their place you get two ordinary clumps, two plain piles of dots sitting behind the two openings, exactly what you'd expect from little balls fired through two doors. The wave is gone. The arithmetic of de Broglie no longer has anything to describe. By choosing to know the path, you destroy the pattern that only existed when the path was unknown. Now here is where almost every telling of this story goes wrong, and where I want to be very careful with you, because the wrong version is seductive and it gets repeated everywhere. The wrong version says the electron knows it's being watched. That observation requires a conscious observer, that somewhere in the chain a mind has to look, and the looking of that mind is what reaches into the world and freezes the particle into a single, definite path. People love this version. It feels profound. It seems to put human awareness at the very center of physical reality. But it isn't what happens. And the true reason is karma, and it doesn't need you or me or any mind at all. What kills the pattern is not a mind, it's entanglement. When the detector registers which slit the electron used, the detector and the electron become bound together, their states woven into one. The which path information and the simple fact of left or right gets stamped into the detector, and through the detector it begins to spread outward into the surrounding world, into stray particles and faint warmth, and all the countless tiny disturbances that make up an ordinary environment. The information leaks, it becomes in principle knowable, and that is enough. That alone destroys the interference. No one ever has to read the detector. No one has to glance at the dial. The record simply has to exist somewhere in a way that could, in principle, be recovered. This has a name and a quiet history. It's called decoherence. A physicist named H. Dieter Zeh worked it out in 1970, and later Wojciech Zurek developed it further, and between them they replaced the mysticism with something far more honest. The observer was never a person. The observer is the environment. The observer is any process that carries away which path information and entangles the particle irreversibly with the wider world. The instant that happens, the delicate overlap of possibilities that made the wave pattern can no longer hold itself together. The pattern doesn't need a witness to die, it only needs to leave a trace. It's a strange comfort, isn't it? The universe is not waiting on your attention. It is not watching to see if you're watching. It simply keeps its own books, and the moment a fact about a particle becomes written down anywhere, in a detector, in a wisp of heat, in the trembling of a single other atom, that writing down is the whole of what we ever meant by measurement. No magic, no consciousness, just information becoming real and spreading where it can't be called back. The control over all of this has only grown finer with time. In 2013, an Italian team, Bach and his colleagues, built a double-slit apparatus where they could open and close each slit on command, send electrons through one at a time, and watch each single detection arrive in real time, in the moment as it happened. They could choose, electron by electron, which doors were open. They could build the pattern up and watch it form before them, a living confirmation of everything Jönsson and Tonomura had seen, now with a dial in their hands. And so we arrive back at that question hanging over your bed, the one I asked you to drift toward rather than chase. If it's information that matters and not minds, then the door that seemed closed swings open again, because information is a thing that can be handled, recorded, moved, and, in principle, erased. So here is the question that has been drifting through the room while we talked about the double slit. We said the pattern vanishes not because a conscious mind chose to look, but because information about the electron's path became real somewhere, written into the physical fabric of the detector, inescapable. And we said information, once written, cannot be called back. But what if it could? What if you could build an experiment where the which path information is written and then gently, precisely rubbed out again? Not by a mind deciding not to look, but mechanically, genuinely erased from the record of the world? Would the interference come back? This is not a thought experiment I am inventing for you to lull you to sleep. This is an experiment that was done in a laboratory with real equipment, real photons, and results you can read in a journal. And the answer it gave is one of the strangest true things in physics, made stranger still by the fact that the popular telling of it gets the strangeness entirely wrong. Let's drift into it. Before there was the experiment, there was the thought. The conceptual parent of everything we are about to cover is a proposal by John Archibald Wheeler, one of the great architects of how physicists talk about quantum mechanics, the man who coined the word black hole and spent a long career insisting that the universe is, at its bottom, made of information rather than substance. In 1978, Wheeler described what he called the delayed choice experiment. He wanted to press on a particular discomfort in the standard picture. The ordinary way of telling the story goes like this. A photon, a particle of light, encounters a half-silvered mirror, which means a mirror that does only half the job. It reflects some light and lets the rest pass through. The photon, being quantum, does not choose one or the other in the classical sense. It behaves as if it went both ways, as if it split and took both paths simultaneously, and when those two paths are brought back together and allowed to interfere, you see the signature fringes of a wave. Now suppose you decide, after the photon has already passed the half-silvered mirror, whether or not to bring the paths back together. If you bring them together, the photon behaves as though it always traveled both paths as a wave. If you do not bring them together, if you intercept one path with a detector, the photon behaves as though it always traveled just one path as a particle. It gives you a definite location, not a wave. Wheeler's observation was precise and unsettling. The photon, according to the quantum description, commits to the shape of its behavior, wave or particle, only when you know which one the experiment will demand. And since the experiment's final configuration can be chosen after the photon has apparently already started traveling, it seems as though the particle is somehow responding to what the experimenter will decide in the future, as though the past is being arranged from the future. Wheeler was careful not to say it was time travel. He was pressing on something more subtle. He wanted physicists to sit with the discomfort of what it means to say a particle took a particular kind of journey before the journey is complete, before the context that gives it meaning is fully set. The journey's nature, he argued, is not settled until the experiment closes. This remained a thought experiment for almost 30 years. The first genuinely convincing realization of it in hardware came in 2007, when Alain Jacques and his colleagues in France built a Mach-Zehnder interferometer, an apparatus that uses two half-silvered mirrors and two full mirrors to split a beam of light along two paths and then recombine it very precisely so you can watch the interference or interrupt it. Jacques and his team connected the final beam splitter, the component that decides whether to recombine the paths, to a fast quantum random number generator. The generator's output was triggered only after the photon had already entered the interferometer. So the decision of whether to combine the paths or not was made by a genuinely random process, operating after the photon had passed the point where it would, classically, have needed to commit. The results matched quantum mechanics exactly. When the final beam splitter was in, interference appeared. When it was out, a definite detection point appeared with no interference. The photon's behavior tracked the final configuration, even though that configuration was chosen after the photon had crossed the entrance of the apparatus. Wheeler's discomfort was validated experimentally with photons and a random number generator moving faster than the photon's own travel through the device. And that is where the story, in the popular version, usually ends, with the breathless suggestion that the future reaches back and arranges the past. which makes for a magnificent feeling of mystery, but is not quite what happened. What happened is stranger and tidier. Now, imagine you have not just one photon, but two, a pair of photons born together from a single event, sharing what physicists call entanglement. When two particles are entangled, they share a quantum state. What you learn about one tells you something about the other, even when they are far apart. The two photons are not in separate states that happen to be correlated, the way two gloves in a pair are matched but independent. Their description is genuinely joint. You cannot write down the state of photon 1 without also writing down photon 2. They are, in the language of the mathematics, a single system that happens to be spread across two locations. In the year 2000, a team of physicists, Yoon-ho Kim, Rong-yu, Sergei Kulik, Yanhua Shih, and Marlon Scully, performed an experiment in Maryland that became one of the most discussed and most misunderstood experiments in recent physics. It is called the delayed choice quantum eraser, and it works like this. You generate pairs of entangled photons. For each pair, one photon, call it the signal photon, travels toward a screen. The other photon, call it the idler, travels in the opposite direction toward a set of detectors. The signal photon passes through a double-slit arrangement. Whether it builds an interference pattern or two clumps depends on whether which path information is available. But here is the twist. The which path information is encoded not on the signal photon itself. It is encoded onto the idler, the entangled partner, which is traveling away in the other direction. Because the two photons are entangled, the idler carries the which path information of the signal. If you measure the idler in a way that reveals which path the signal took, that information exists, and the signal photon will contribute to a clumpy distribution. If you measure the idler in a way that destroys the which path information, if you erase it, then in the appropriate subset of data, the signal photon will show interference, and the choice of how to measure the idler, whether to preserve or erase the which path information, is made after the signal photon has already hit the screen. Let that sit for a moment. The signal photon lands on the detector. Its position is recorded. At this point, the signal photon is done. It has made its mark. And then later, the idler arrives at its own detectors, and the experimenters decide whether to erase the idler's which path information or to read it. The signal photon already landed. The record is already made. Yet what happens at the idler after the fact seems to determine what pattern the signal photons had. This is the version that makes people say you can change events that already happened. This is the version that gets quoted on websites and in late-night conversations as evidence that time flows backward, that consciousness reaches into the past, that the universe is responsive to intention in ways classical physics would never allow. This is not what happened. Here is what actually happened, and it is more interesting. The signal photon's raw data, the full set of positions where signal photons landed, unfiltered, all of them together, shows no interference pattern, none. Two clumps, or more precisely, a smooth distribution that carries no wave signature at all. If you look only at the raw signal photon data, you see nothing that suggests interference is hiding in there. You see ordinary positions. The interference only appears when you do something called coincidence counting. You take the record of where each signal photon landed and you sort that record based on what the corresponding idler photon did. You keep only the signal photons whose idlers hit a particular detector. One of the detectors in the idler's path that corresponds to erasing the which path information. When you pull out that subpopulation and look at only them, they form an interference pattern. The other subpopulation, the signal photons whose idlers were measured in the which path preserving way, form an anti-correlated clumpy pattern. Add the two subpopulations together and you get back the original smooth, non-interfering total. What does this mean? It means the interference was not created by the later choice of how to measure the idler. The interference was always there, in the structure of correlations between signal and idler, encoded at the moment the entangled pair was born. The later measurement of the idler does not reach back in time and rearrange the signal photons past. It does something more modest and more profound. It gives you a sorting key. The full story of the signal photon, keys which subset it belongs to, what pattern it is part of, was written at the moment of the photon pair's creation. All of it. The correlation was complete from the start. The experimenters, by choosing how to measure the idler, are not editing history. They are choosing which chapter of a book that was already fully written to read first. The other chapters are still there, in the data, perfectly consistent, and when you put them all together, the book makes sense. This is, I want to suggest to you, considerably more unsettling than time travel. Time travel would mean the world is a machine with a rewind button. What the quantum eraser shows is that the world does not commit to a single, complete description till all the relevant context is in. Not because minds are shaping it, but because the correlations between entangled systems are irreducible. You cannot tell the story of one photon without eventually accounting for the other. The two particles were a single system divided in space, and the outcome, the pattern, is a property of that whole, not of either part alone. The book was whole before you opened it. You just needed both volumes to read any given page. There is a guardian standing over all of this, a theorem that prevents the obvious misuse of this phenomenon, and it is called the no signaling theorem. It is worth knowing its name and its argument because it is the thing that puts a clean floor under the weirdness. The thing that tells you exactly how far the strangeness goes and no further. Here is the argument in plain terms. Suppose you and a friend share a large number of entangled photon pairs. You are in one room, she is in another, and for the sake of argument, let us say the rooms are far apart. You measure your photons, she measures hers. Could she, by choosing what kind of measurement to make on her photons, send you a message that you would receive faster than light could travel between the rooms? The answer is no, and the reason is clean. Your raw data, the positions where your photons land, looks the same regardless of what she does with her photons. The correlations only become visible when you bring your data and her data together and compare them. That comparison requires a classical channel which cannot go faster than light, so there is no way to extract a signal from entanglement alone. The sorting key only becomes meaningful once the two records are merged, and merging them is a classical, ordinary process that obeys the ordinary speed limit. This is why the quantum eraser is not time travel. Time travel would require that the choice made later creates a visible difference in the earlier data, but the earlier data looks identical regardless. The difference only appears in the correlated structure, which you can only access by comparison after both halves have been gathered. The universe is not handing you a message from the future. It is giving you a correlation that was always present, which you can only read fully once you hold both ends of it. This matters for another reason. One of the most famous complaints in the history of physics, a complaint leveled by Albert Einstein, who found the implications of quantum mechanics deeply troubling, was that quantum entanglement seemed to imply a spooky action at a distance, some kind of instantaneous influence transmitted between the two particles regardless of how far apart they were. Einstein didn't like this. He felt it contradicted relativity's firm insistence that nothing travels faster than light. He argued with Boris Podolsky and Nathan Rosen in 1935 in a paper everyone now calls EPR, that the apparent strangeness of entanglement simply showed that quantum mechanics was an incomplete description, that there must be hidden facts, pre-existing values carried by the particles from the beginning, which merely get revealed when you measure them, the way a pair of gloves has always had one left and one right, even before you open the box. The quantum eraser, understood correctly, shows why that glove picture fails. The correlations are not like gloves. They cannot be explained by pre-existing hidden values. The structure of the data is genuinely irreducible to any classical picture of two separate particles carrying matching instructions from their shared origin. The book was not pre-written in the classical sense. The correlations exceed what any classical pre-assignment could produce. And that conclusion, that the correlations are real, are non-classical, and cannot be explained by hidden instructions, is not just a philosophical interpretation. It is a mathematical result, and it has been tested in the laboratory with increasing rigor and completeness over several decades. That story belongs to the next experiment we need to visit together. But first, rest here for a moment in what the eraser actually taught. The experiment is not about consciousness. It is not about changing the past. It is about entanglement as a kind of inseparability, a refusal by nature to allow a complete local description of either particle in isolation. The which path information does not live in the signal photon. It lives in the relationship between signal and idler in the full two-photon system. And that system was whole from the start. What you choose to measure later determines which slice of that whole you expose. You are not sculpting the universe. You are unfolding a map that was already drawn. Sleep is a little like this, in a way. The night does not rearrange what happened in the day. But the way you turn it over, the angle from which you approach it in the quiet behind closed eyes, reveals structures that were always there, waiting for the right kind of attention. No editing, only disclosure. I like that image. I hope it settles gently into wherever you are right now. Your bed, your train, your chair with the lamp still burning low. The question the eraser leaves open is sitting right there in the word we had to use. Entanglement. Two particles sharing a description so completely that measuring one tells you something about the other, regardless of where they are. But how complete is that sharing? How far does it reach? And more importantly, can it be made precise? Not as a vague feeling of mystical connection, but as a number, a hard mathematical constraint, something that can be measured and compared against what any ordinary classical picture of the world would predict. This is the territory John Stuart Bell entered in 1964. Bell was an Irish physicist working at CERN, the European Particle Physics Laboratory, and he had a particular kind of patience for questions that other physicists had quietly set aside. The EPR argument, the gloves argument, the hidden instructions argument had been sitting in the air since 1935 without anyone being able to test it. It was a philosophical dispute. Einstein's side said the quantum description must be incomplete, that there must be hidden variables carrying the particle's predetermined properties. The quantum mechanics side said the correlations are real and irreducible and no hidden variables can explain them. But nobody had found a way to turn that dispute into an experiment that could settle it. Bell found the way. His insight was this. Suppose, as Einstein suggested, that each particle in an entangled pair carries a set of hidden instructions, a complete list of how it will respond to any measurement you might make, decided at the moment the pair was created and shared between them. These hidden instructions are local. Each particle's instructions travel with that particle and don't require any ongoing connection to its partner. This is what physicists call local hidden variables, or more broadly, local realism. The idea that properties of things are definite and local, existing in the things themselves before any measurement is made. If local hidden variables exist, Bell showed, then the correlations between measurements on the two particles must obey a mathematical constraint. The constraint takes the form of an inequality, a statement that says certain combinations of measurement results over many trials can add up to no more than a particular number. For the version of the inequality that became most experimentally practical, derived by John Clauser, Michael Horn, Abner Shimoni, and Richard Holt, and known as the CHSH inequality, the classical local realist bound is 2. Any theory with local hidden variables, however cleverly constructed, must produce a combined correlation score of at most 2. Quantum mechanics predicts something larger. The quantum mechanical prediction for the maximum correlation achievable by an entangled pair, derived by a mathematician named Boris Tyrelson, is 2 times the square root of 2, which works out to approximately 2.828, not enormously larger than 2, but larger in a precise and testable way. The gap between 2 and 2.828 is where Bell's inequality lives, and it is the gap that separates a world with local hidden variables from the world quantum mechanics describes. Now you test it, you make pairs of entangled particles, you send one to each of 2 detectors. At each detector you choose, randomly, one of several orientations in which to make your measurement. You record the results, you calculate the CHSH score from your data, and you ask, does it exceed 2? The first experiment to seriously tackle this was performed by John Clauser and Stuart Friedman in 1972, using entangled photons. They saw a violation. Their result exceeded the classical bound. But the experiment had limitations, what physicists call loopholes, alternative explanations that could not quite be ruled out. Perhaps the detectors were not measuring a truly representative sample of all the pairs produced. Perhaps there was some subtle communication between the 2 sides of the experiment that the setup hadn't ruled out. The experiment needed to be made tighter. In 1982, Alain Aspect and his colleagues Jean Dalibard and Gérard Roget in Paris performed what became the landmark Bell test of that era. They used entangled photons and, critically, they used analyzers whose orientations were switched rapidly, randomly, while the photons were in flight between source and detectors. This meant that no signal moving at or below the speed of light could carry information about the setting on one side to the measurement being made on the other. The locality loophole, the possibility that the 2 detectors were subtly communicating, was significantly tightened, and the violations were clear. The CHSH score landed near 2.7, comfortably above the classical ceiling of 2, and fully consistent with quantum mechanics. But there were still loopholes. The detection efficiency was not high enough to rule out the possibility that the pairs being detected were an unrepresentative sample, what is called the detection loophole. And the speed of the switching, while fast, was not truly random in the strict sense required. For 33 years after Aspect's experiment, physicists worked to close the remaining loopholes. 2 separate loopholes had been closed individually in different experiments, but never both at once. The experiment that finally did both simultaneously in a single run appeared in 2015. It was led by Bas Jönsson and his colleagues at the Delft University of Technology in the Netherlands. Their approach was different from the photon-based experiments. They used electron spins trapped in small diamonds. 2 diamonds, positioned 1.3 kilometers apart in separate buildings on the Delft campus. The electron spins were entangled by a protocol involving the emission and detection of photons. The entanglement was established, and then immediately the 2 spins were measured locally before any light speed signal from one side could reach the other. Because the detectors were 1.3 kilometers apart, the time it would take a signal moving at light speed to cross that distance was longer than the time between establishing the entanglement and completing the measurements. The locality loophole was closed by geography and timing, and the detection efficiency with electron spins was high enough to close the detection loophole at the same time. The CHSH score they measured exceeded the classical bound. Local realism was ruled out, not as an interpretation, not as a philosophical preference, but as a matter of experimental result, with both major loopholes closed simultaneously for the first time. 2 other groups published loophole-free results in the same year. the Vienna group under Mariana Justina, and the NIST group in Boulder, Colorado under Lyndon Schaum, using high-efficiency photon detectors. 3 independent laboratories, 3 different implementations, all in 2015, all giving the same answer. The classical world with local hidden variables does not match what is observed. The physics community took note in the way physics communities take note of things, slowly, and then all at once. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their experimental work on entangled photons and the violation of Bell's inequalities. It was a recognition that something genuinely foundational had been established, not a curiosity, not a clever trick, but a result that forces a revision of what we mean by the physical world. There is a version of the Bell story you may encounter that says, Einstein was proven wrong by these experiments. I want to be careful with this because it is partly true and partly misleading, and the distinction matters for sleeping with a clear conscience. What was proven wrong is Einstein's local realism, the specific picture in which particles have definite, pre-existing properties and can only influence each other through signals that travel at or below the speed of light. That picture, in its precise form, does not survive the Bell tests. The world is not locally real in the way Einstein hoped, but Einstein's other great insistence, that no signal, no usable information, can travel faster than light, survives intact. The correlations measured in a Bell test are real, they exceed what classical local realism permits, and yet they cannot be used to send a message faster than light. The no-signaling theorem we met in the quantum eraser story applies here with equal force. When you measure the spin of one electron in Delft and your partner measures the other spin in Delft too, 3 kilometers away, the correlation that appears in your joint data does not allow either of you to send a message to the other that would arrive before light could cross the distance. You cannot communicate with entanglement alone. You still need a classical channel to compare notes. So the world is not locally real, but it is also not a world where information travels faster than light. You have to give up one thing: the comfortable picture of particles carrying predetermined properties through space like little labeled packages. But you get to keep the speed limit. Einstein was wrong about local realism and right about the speed limit. Both things are true. What you cannot keep is the comfortable picture itself, the solid, definite local world your senses report. The world of objects with properties that exist before you look at them, affecting each other only through contact or fields that propagate at finite speed. That world is not the world the experiments are describing. The correlations are real, and they are stronger than any local classical story can produce. Something non-local is woven into the fabric of things. We just can't use it as a telephone. One of the most remarkable subsequent experiments took the Bell test and pressed it back to the edge of the observable universe. In 2017, a team including Johannes Hansteiner, working with Anton Zeilinger's group, performed what they called a cosmic Bell test. The question they were asking was this: even granting all the loophole closures of 2015, there is a philosophical escape hatch remaining. Suppose the detector settings on the 2 sides were not truly randomly and independently chosen. Suppose the universe from the very beginning had arranged the initial conditions of everything, including the settings that the experimenters would choose, in such a way as to mimic quantum correlations without actually violating local realism. This is called the freedom of choice loophole, or sometimes the superdeterminism loophole, and it is unfalsifiable in the absolute sense, but it can be pushed further and further back in time until it requires a conspiracy of cosmic proportions. The cosmic Bell test pushed it back very far indeed. The detector settings were chosen not by random number generators on the table in the laboratory, but by the color of photons arriving from 2 distant quasars, one about 600 light-years away and one about 12 billion light-years away. The color of a photon from a quasar is determined by astrophysics at the quasar itself, billions of years ago. If any hidden variable theory wants to explain the observed correlations by claiming that the detector settings were prearranged to match the particle's hidden properties, it now has to arrange that conspiracy at least 12 billion years in the past. The experiment showed violations of Bell's inequality even with these ancient light sources setting the detector choices. The correlations held, local realism still failed. You do not have to believe in 12 billion year conspiracies. The universe is not that tidy in the conspiratorial sense, and it is not that tidy in the local realist sense either. What it is something considerably stranger. A place where correlations between distant things can be stronger than any local account of those things can explain, and yet cannot be used to send a signal, and yet are perfectly real, and yet do not require consciousness or observation by any mind. What they require, what all 5 of these experiments require at the level of the load-bearing concept, is information. What can in principle be known in the full physical sense, encoded in matter irreversibly, leaving a trace capable of being read. Not what a person knows, not what any conscious being has noticed, what the universe keeps as its own record. That thread, information as the fulcrum, runs quietly through everything we have visited tonight. The interference pattern in the double slit lives or dies by whether which path information is available in principle. The quantum eraser reveals that the correlations between entangled photons are a complete, whole, pre-existing joint description, accessible only when you have sorted by the full context. And the Bell test shows that those correlations exceed what any local account, any account based on pre-existing separate properties, can produce. Something non-local is here, and it obeys rules. They are just not the rules intuition assembled from a lifetime of touching and lifting solid things. Your bed is solid, the pillow is solid, the dark behind your closed eyes is, for all ordinary purposes, the darkness of a world that behaves exactly the way your senses report it does. Walls are solid, coffee is warm, objects stay where you put them. None of this is contradicted by Bell's theorem. The non-locality that violates Bell's inequality is real, but it operates at a scale and in a register that classical objects made of enormous numbers of particles whose quantum correlations have long since washed out into thermal noise do not display. The strangeness is not hidden from you by some failure of attention. It is simply present at a different scale, a scale where single particles and carefully prepared entangled pairs can be isolated and measured before the environment has had time to dissolve their correlations. Once an object is large enough and warm enough and surrounded by enough other atoms, the quantum correlations smear out into the classical averages we experience as solidity. This process, decoherence, is the bridge between the quantum world and the everyday one, and it is why your bed does not exhibit interference fringes, even though it is, at the level of its quarks and electrons, a quantum system. But the strangeness does not disappear. It simply moves somewhere you can't reach with your hands. It is there, in the structure of things, in the correlations that no local account can explain, in the phase relationships that persist, in carefully protected quantum systems, waiting to be examined by laboratories with very clean hands and very good timing. Before we leave the Bell story and move on, there is one more image I want to leave you with because it is one of the most clarifying things the experiments have produced. The CHSH score for a classical local realist world cannot exceed 2. The quantum mechanical bound, Sorelson's bound, is 2 times the square root of 2, approximately 2.828. The experiments land near 2.8, comfortably below 2.828, right where quantum mechanics said they would be. That number, 2.828, is not arbitrary. It is the maximum correlation the structure of quantum mechanics permits. It is a hard ceiling built into the mathematics of Hilbert spaces and unitary transformations, the formal machinery of quantum theory. And it is interesting that it is not unlimited, that quantum correlations, while exceeding the classical bound, do not reach the absolute maximum that logic alone would permit if you ignored the structure of quantum mechanics. There is a version of non-local correlations imagined by mathematicians that would allow a score of 4. Quantum mechanics does not go there. It goes to 2.8, 2.8, and no further. The universe is strange, but it is not infinitely strange. It has a shape, it has a texture, and that texture, those precise numbers, those specific violations and specific non-violations, are the territory the experiments are mapping one careful result at a time. Close your eyes on that if you like. The universe has a precise ceiling on its strangeness, and the experiments have measured it, and it is 2 times the square root of 2. That is not nothing. Somewhere in the data from Delft, from Vienna, from NIST, from Paris, encoded in the records of thousands of photons and electron spins, carefully caught and compared, is the signature of a world that does not keep all its facts locally, that does not preassign its properties, that writes its correlations into the joint description of systems rather than into each part separately, and the writing is precise, and it obeys rules, and the rules are knowable. There is, I find, something profoundly restful in a constraint that is clean, not the restfulness of simplicity. The quantum world is not simple. The restfulness of a boundary you can actually put your hand against and feel, instead of the vertiginous anxiety of a world with no rules at all. The universe is not making things up as it goes. It is playing a game with rules more intricate than intuition built for, but it is playing it consistently, and the rules are the same in Delft as they are in Vienna, as they are in your dark room with the lamp turned low. Let the measurement outcomes settle in the correlations. Let the CHSH score be what it is. Let the 2.828 be the ceiling of the strangeness, reliable, fixed, proven in 3 laboratories in a single year. And now let me ask you something. The Bell tests leave planted. We have talked, in both movements tonight, about measurement as a process that extracts information, that forces a definite outcome from a cloud of possibilities. But we have not yet asked, what happens when measurement comes so fast, so continuously, so relentlessly, that the quantum system has no gap in which to change at all? The Bell tests showed us that correlations between distant particles exceed what local realism permits. The next experiment asks something different. It asks whether the act of measuring, applied not to 2 separated particles, but to a single system over and over and over again, can freeze that system in place, can prevent the universe's own tendency toward change from having anywhere to go. It is, in its way, the strangest of the 5 experiments, not because the mathematics is forbidding, but because the image it leaves behind is so direct, so physical, so easy to feel in the body. A watched pot, it turns out, never boils. Not metaphorically, measurably. In a specific laboratory with a specific kind of ion and a specific number of pulses per second. But that is where we are going next. For now, let the Bell inequalities rest in your chest like a solved equation, clean, strange, true. The non-local correlations are real. They cannot send a signal. They cannot be explained by hidden instructions. They are a feature of the world, not a bug in the theory. And they are, in the quiet of wherever you are right now, woven into every electron, in every atom, in every molecule of the blanket over you, whether you are measuring it or not. And so we arrive at John Stuart Bell. It is 1964. Bell is a theoretical physicist at CERN, the particle physics laboratory near Geneva, and he has been quietly turning over a problem that had been sitting in the foundations of quantum mechanics for nearly 30 years, a problem that most physicists considered either solved or not worth worrying about. Einstein had worried about it. Niels Bohr had insisted there was nothing to worry about. And for the most part, the physics community had sided with Bohr and moved on because quantum mechanics worked, and working was enough. But Bell was not satisfied with enough. The problem went back to 1935 to a paper Einstein wrote with Boris Podolsky and Nathan Rosen, the EPR paper, as it came to be called. The argument went something like this. Quantum mechanics says that two particles can be entangled, meaning their properties are correlated in a way that only resolves when one of them is measured. Before measurement, neither particle has a definite value for, say, its spin. Measure one and it snaps into a definite state, and instantly the other one snaps into the correlated state, no matter how far apart they are. Einstein found this deeply troubling. He had spent his career establishing that nothing travels faster than light, that causes always precede effects, that signals cannot leap across space without crossing the space in between. And yet quantum mechanics seemed to suggest that the moment you measured one particle, something reached across however many miles or light years, separated them, and told the other particle what to be. Einstein called this spooky action at a distance, and he said, with characteristic directness, that he did not believe it. His alternative was the idea that the particles had definite properties all along, hidden perhaps from our instruments, but real, settled, local. They were carrying a kind of secret instruction set coded at the moment they were created together that told each of them what answer to give when measured, no signal needed to cross any distance. The answers were already in the envelope. You just hadn't opened it yet. This is what physicists call local realism. Local, meaning each particle's behavior depends only on what is nearby, nothing faster than light required. Realist, meaning properties exist before and independently of measurement. It sounds, if you let it settle for a moment, deeply reasonable. It sounds, in fact, like common sense, which is precisely what made Bell's result so devastating, because Bell proved that common sense was wrong. Not vaguely, not philosophically, mathematically, precisely. He showed that any theory built on local realism, any theory at all, not just quantum mechanics, but any theory you might someday invent, must obey a certain mathematical inequality. The inequality constrains how correlated the measurement outcomes of two distant particles can be if those particles are carrying hidden local instructions. If you measure the spin of particle A along one angle and the spin of particle B along a different angle, and you do this over and over for thousands of pairs, and compare the results, the pattern of agreements and disagreements has a ceiling, a maximum correlation. Local realism draws a line and says, you cannot go above this. The line in the version of the test most often used, the CHSH version, named for Clauser, Horn, Shimoni, and Holt, gives a classical bound of 2. If you work out the number that summarizes the correlations across 4 different measurement angle combinations, local realism says that number cannot exceed 2. It might be less, it cannot be more. Quantum mechanics predicts it can. Quantum mechanics predicts a value up to 2 times the square root of 2, which works out to approximately 2.828. This limit is called the Tserelson bound, after Boris Tserelson, who proved in 1980 that this is the highest quantum mechanics itself allows. So there is a gap, a specific, measurable numerical gap between the world that local realism describes and the world that quantum mechanics describes. And the question Bell had opened was, which number does nature actually give? For years, this was a thought experiment, a beautiful one, but a thought experiment nonetheless. The particles and the measurements it required were very difficult to arrange in a real laboratory, and there were gaps, loopholes, physicists called them, that allowed a stubborn local realist to argue that the results, even if they violated the inequality, might not be decisive. Maybe the detectors were not efficient enough and were only catching a biased sample. Maybe the measurement settings were chosen in a way that the particles could somehow have anticipated. The first person to actually do the experiment was John Clauser, working with Stuart Friedman at Berkeley In 1972, they used pairs of photons, particles of light, emitted by calcium atoms, and they measured the polarization of each photon along different angles. The result violated Bell's inequality. The number came out above 2. Local realism, their data suggested, was in trouble, but the loopholes remained. Then in 1982, Alain Aspect and his colleagues Dalibard and Roger, working in Paris, did something cleverer. They did the experiment with a crucial addition: the measurement settings. The angles at which each photon's polarization was measured were changed randomly while the photons were in flight, after they had already left the source. This closed the so-called locality loophole. If the particles were carrying hidden instructions, those instructions would have had to be set before the particles left, and the instructions couldn't know in advance what angle the detector would choose, because the angle was chosen randomly after the particles were already on their way. Aspect's result still violated the inequality. The correlations were still above 2. Local realism was still losing. But there were still loopholes, particularly the detection loophole. The fact that not every pair of photons was successfully detected, and one could argue that only the detected ones happened to give correlated results, while the undetected ones would have rescued local realism if only we could have seen them. And so the work continued for decades, refining the experiments, tightening the constraints, closing one loophole and then another. Each improvement was also an extraordinary feat of engineering. Keeping quantum systems isolated, keeping measurement settings random and independent, getting detection efficiencies high enough that the undetected pairs could no longer plausibly explain the violation. And then came 2015. In 2015, 3 separate teams working independently on different continents with different particles and different methods each closed both the locality and the detection loopholes simultaneously for the first time. These are called the loophole-free Bell tests, and they are among the most carefully designed experiments in the history of physics. The first was led by Bas Henson and his colleagues at Delft in the Netherlands. They did not use photons, they used electron spins, the tiny intrinsic angular momentum of individual electrons trapped in diamonds. Real diamonds, small ones, used as quantum traps because the lattice of carbon atoms can hold an electron spin in isolation remarkably well. The 2 diamonds were 1.3 kilometers apart. The measurement settings were chosen randomly and independently at each end, fast enough that no signal traveling at the speed of light could carry information between the 2 locations before the measurements were complete. The detection efficiency with electron spins is high enough that the detection loophole does not open. The result violated Bell's inequality. Both loopholes closed at once. There was nowhere left for local realism to hide. The second loophole-free test in 2015 was performed by Marissa Giustina and her team in Vienna, using photons with improved detection efficiency. The third was done by Lyndon Schalm and colleagues at NIST, the National Institute of Standards and Technology in the United States, also with photons and a carefully randomized measurement protocol. All 3, same year, same result. The number came out above 2, near the quantum prediction of 2.828. Local realism, the idea that particles carry hidden definite properties and that nothing moves faster than light between them, was ruled out by experiment, not by argument. The Nobel Prize in Physics for 2022 was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for this body of work. Zeilinger, based in Vienna, had spent decades extending entanglement experiments, pushing entanglement across longer distances, demonstrating quantum teleportation, and laying the groundwork that would eventually feed into quantum cryptography and quantum communication. The Nobel citation recognized what the decades of experiments had established, that entangled particles violate Bell's inequalities, and that this violation is a feature of the real world, not an artifact of imperfect apparatus. Take a breath here, let that settle, because there is a version of this story that is easy to tell and wrong to believe, and this is the moment to slow down and separate them. The wrong version says, Einstein was proven wrong, entanglement sends signals faster than light, the universe is non-local, and you can use entangled particles to communicate instantly across any distance. This version is dramatic, and it circulates, and it is not what the experiments show. Here is what they actually show.
Local realism is dead. You cannot keep both parts of it simultaneously. You cannot have particles with pre-existing definite properties and a universe where nothing influences anything faster than light. At least one of these must go. The experiments tell you that. They do not tell you which one to sacrifice, and different interpretations of quantum mechanics make different choices, but the combination is ruled out.
What survives, completely intact, not a scratch on it, is Einstein's insistence that no usable signal can travel faster than light. This is the no signaling theorem, and it is a mathematical consequence of quantum mechanics itself. Here is the critical subtlety. When you measure your entangled particle and get a result, and your partner far away measures their particle and gets a correlated result, neither of you, looking only at your own results, can tell whether the other one has been measured yet. Your results, taken alone, look completely random. The correlation, the pattern that violates Bell's inequality, only appears when you bring both sets of results together and compare them. And bringing them together requires a classical channel, a phone call, an email, a letter, something that cannot move faster than light. So the correlation is real, and it is non-local in the sense that it cannot be explained by local hidden variables, and yet it cannot be used to send a message. The two things, non-local correlation and no faster than light signaling, coexist, which feels almost paradoxical until you understand that correlation is not the same thing as communication. Two clocks set to the same time in the same room and then carried to opposite sides of the world will always agree when you compare them. That correlation does not mean one clock is sending a signal to the other. The quantum case is far stranger than synchronized clocks, but the structural point holds. Correlation without a readable signal is not a phone line. Einstein's no faster than light rule survives. Local realism does not. Those are two separate things, and keeping them separate is the honest telling of what Bell's theorem proved. Now, if you have been lying in the dark turning this over, there is a question you might be quietly constructing. It goes something like this. Fine. Perhaps the particles are not carrying hidden instructions. Perhaps local realism is wrong. But could the universe be conspiring? Could it be that the random number generators used to choose the measurement angles in 1982 or in 2015 were themselves, through some deep structure of physics we don't understand, correlated with the particles in a way that rigged the results? This is called the freedom of choice loophole, or the cosmic conspiracy loophole, and it sounds at first like the kind of thing only a very determined skeptic would reach for. But physicists take it seriously because the logic of Bell's theorem requires that the measurement settings be genuinely independent of the particles being measured, and proving genuine independence is surprisingly difficult when everything in the universe shares a common past. In 2017, a team including Johannes Hansteiner pushed back against this loophole in a remarkable way. They ran what became known as the cosmic Bell test. Instead of using a quantum random number generator or a physical random process to choose the detector settings, they pointed two telescopes at two different quasars, active galactic nuclei among the most luminous objects in the universe, and used the color of the light arriving from those quasars to determine the measurement settings in real time. The quasars were roughly 600 light-years and 1,900 light-years away respectively. The light arriving from them had been traveling for that long, hundreds of years, in some cases approaching 1,000 years, before it hit the telescopes, and in the same instant determined which angle the detector would use. This means that for the detector settings in this experiment to have been prearranged in conspiracy with the particles being measured, the conspiracy would have had to be set up before that quasar light was emitted, before Columbus, before the printing press, before the Black Death. The result still violated Bell's inequality. If you want to save local realism through the freedom of choice loophole, you now have to argue that the conspiracy goes back at least 600 to 1,900 years, and the door is still technically open by a crack. You can always push the conspiracy further back, push it back far enough, and you reach the Big Bang, a single common origin for everything, from which all subsequent correlations might in principle have been prearranged. This is the point where most physicists and most people find that local realism has become more expensive to defend than to abandon. When the only way to save your assumption is to propose a cosmic conspiracy woven into the first moments of time, the assumption has stopped doing useful work. And this brings us to the unifying thread, the thing that the quantum eraser and the double-slit and the Bell tests are all saying in their different ways. The load-bearing concept here is not consciousness. It is not the idea that minds create reality. It is information. What can in principle be known, what is in principle encoded somewhere in the physical world, is what determines which kind of reality you get. When which path information is available in the environment, interference vanishes. When it is erased, correlations in the data reveal themselves. When two particles are entangled, their combined state carries information that cannot be decomposed into separate local stories. The world is not built out of solid, definite things, sitting in definite places with definite properties waiting to be found. It is built out of correlations, potentials, and information structures that resolve into specific outcomes when they become irreversibly entangled with their surroundings. That is the actual strange thing. It is stranger than consciousness causing collapse in a way, because it does not leave any comfortable foothold for the self at the center of the mystery. The electron is not responding to you, it is responding to a physical process of information transfer that happens to include a detector, which may or may not be connected to a human eye. There is one more thread worth pulling before we leave Bell. You will remember from the first movement the image of electrons building an interference pattern one dot at a time, and the observation that this had been demonstrated not only with electrons, but with increasingly large objects, atoms, then molecules. The Vienna group, led by researchers including Fine and colleagues, published results in 2019 showing quantum interference with molecules of approximately 2,000 atoms, weighing around 25,000 atomic mass units. These are not subatomic specks. They are large, complicated objects by any ordinary measure. Macromolecules that would have struck a physicist of the early 20th century as absurdly, impossibly large to show quantum behavior. And they still interfered. The reason we do not see interference in everyday objects, chairs, teacups, the blanket over you, is not that large objects are exempt from quantum mechanics. It is that large objects are constantly, unavoidably, catastrophically entangled with their environments. Every photon that bounces off a chair, every air molecule that touches it, every vibration that passes through the floor creates which path information. The environment is continuously measuring the chair in the quantum mechanical sense of that word, and so the chair's quantum possibilities collapse into definite classical behavior so rapidly that no experiment we can build would catch it doing anything wave-like. The threshold is not size in some absolute sense, it is the rate of environmental entanglement, which scales with size in a way that makes macroscopic objects classical to any practical purpose we might attempt. But the principle holds. Quantum mechanics does not stop applying to large things. Large things just decohere faster than we can detect the interference. It is a quantitative difference, a matter of time scales, not a qualitative one. The chair is, in some deeply formal sense, a quantum object. You simply cannot build an apparatus sensitive enough to catch it being one, because the apparatus itself would disturb it before the measurement was complete. This is not, in the end, a source of despair. It is a source of a particular kind of calm. The rules of the quantum world are consistent and exact and experimentally verified to extraordinary precision. We are not dealing with chaos, we are dealing with a deeper order than the one our senses evolved to report, an order that becomes visible only in very controlled conditions, with very small objects and very careful apparatus. The 2022 Nobel Prize was not awarded for proving that the universe is strange and unknowable. It was awarded for proving precisely to multiple decimal places what kind of strange the universe is. The Bell tests tell you that the solid, local, definite world your senses report is not the fundamental reality. It is an emergent approximation, an extraordinarily good one for the scales at which organisms like us live and operate, but an approximation nonetheless. Underneath it, the entanglements are real and the correlations exceed what any local instruction set could produce, and yet nothing moves faster than light, and nothing in your experience is disrupted because the gap between quantum correlations and classical signals is exactly wide enough that the everyday world runs on the classical surface without ever knowing what is underneath. That gap is not an accident. It is enforced mathematically by the no signaling theorem. The universe arranged itself, or the laws arranged themselves, or however you choose to speak about it, so that the quantum strangeness below is permanently insulated from the classical operations above. You cannot reach down through the insulation and pull up a faster-than-light telegram, but you can do experiments, very careful experiments that probe the boundary from the classical side and find unmistakably that the quantum strangeness is there. 3 teams in 2015, both loopholes closed. The number above 2, local realism, gone. That is the Bell test. Rest here for a moment. The hard mathematics is behind us. What remains, and what we are drifting toward now in the quiet of wherever you are, is perhaps the strangest of the 5 experiments in the sense of feeling it in the body. Not the strangest mathematically, but the strangest as an image, because the Bell test showed us that correlations between distant particles exceed what local realism permits. But the Bell test still involved 2 particles, 2 detectors, 2 distant places. It still involved the act of measurement as something that happens once, decisively, at a specific moment, extracting one answer from a cloud of possibilities. The next experiment takes the act of measurement itself and asks what happens when you make it not once, but again and again and again, faster and faster, so frequently that the quantum system has no room to do anything between one measurement and the next. The answer is, it freezes. Not slowly, not partially, measurably, demonstrably, in a laboratory at NIST with a specific kind of ion and a specific number of pulses per second. The faster you watch, the less things change. Carry it to the limit, and a quantum system under sufficiently continuous observation cannot evolve at all. This effect has a name. It takes its name from a philosopher who lived 2,500 years ago and built a set of paradoxes about motion that seemed on the face of them to prove that nothing could ever move at all. His name was Zeno of Elea. His most famous paradox concerns an arrow in flight. At any single instant, he argued, the arrow occupies a definite position in space. At that instant, it is not moving. Motion requires time, and an instant has no duration. If you can freeze any instant and say the arrow is not moving in that instant, and if time is nothing but a collection of such instants, then when, exactly, is the arrow ever moving? The paradox does not survive contact with calculus. Newton and Leibniz would eventually dissolve it with the concept of a limit. But the image is haunting. An arrow suspended every instant still. Motion, an illusion built from stillness, stacked on stillness. The quantum Zeno effect is the discovery that this image, in a specific and precise sense, becomes true for quantum systems under rapid, repeated measurement. And the man who first formalized this, mathematically, was not a Greek philosopher, but two physicists, Baidyanath Misra and E.C. George Sudarshan, who published their analysis in 1977. Their paper did something elegant. It took the mathematical structure of quantum time evolution, worked out what happens when you interrupt it repeatedly with a measurement, and showed that as the measurements come faster, the probability of the system having changed state approaches zero. In the mathematical limit of continuous measurement, the change is completely suppressed. That is a theoretical prediction. Theories can be wrong. In 1990, a team at NIST, Wayne Itano, Dan Heinzen, John Bollinger, and David Wineland, decided to test it. They used beryllium ions. Beryllium is a light metal, element 4 on the periodic table, and its ions, atoms that have lost an electron and carry a net charge, can be trapped in a small region of space using electric and magnetic fields. This kind of trap, a Penning trap, holds the ion in place so it can be studied with extraordinary precision, and the trapped ion's internal energy levels are extraordinarily well defined. In the experiment, the beryllium ions were prepared in one energy level. Call it the ground state, the quiet state, the state of rest. Quantum mechanics predicts that if you leave the ion alone and shine a specific kind of light on it, it will gradually, over a precisely calculable time, transition to a higher energy state, an excited state. The transition is not instantaneous. It follows a smooth probability curve that climbs over time. Left alone for the full allotted period, the ion would have about a 50-50 chance of having made the transition, which means that if you did the experiment many times, about half the ions would end up in the excited state and half would remain in the ground state. What the NIST team did was interrupt the transition. While the ion was in the middle of transitioning, partway through the process, somewhere in that rising probability curve, they applied a brief pulse of light designed to measure which state the ion was currently in, not to stop it, not to manually reset it, simply to measure it. And quantum mechanics says measurement collapses the state. If you measure the ion during its transition, you force it to be in one state or the other, right now, with the probabilities that apply at that moment. And because the transition starts from zero probability and rises gradually, if you interrupt early in the process, the probability of finding the ion in the excited state is low, and the probability of finding it still in the ground state is high. The measurement, if the ion is found in the ground state, resets the clock. The transition must start over from zero. Do this often enough. Apply measurement pulses rapidly, repeatedly throughout the transition period, and each time you find the ion still in the ground state, you reset the clock. The transition never builds up enough probability to complete. The more measurements, the slower the effective transition rate. The NIST team performed this experiment with different numbers of measurement pulses: 4 pulses, 8 pulses, 16 pulses, spread over the same total time period. With no pulses, the ion transitioned about half the time as expected. With 4 measurement pulses, the transition probability dropped. With 8, it dropped further. With 16, it dropped further still. The more frequently they interrupted the process by measuring it, the more the transition was inhibited. The data matched the quantum mechanical prediction. The quantum Zeno effect was real, measurable, and matched the theory quantitatively, not just qualitatively. Take a moment with that image, an ion sitting in a trap, almost in the act of changing state or daki, and the act of repeatedly asking, "Have you changed yet?" Answering itself with "not yet," each time resetting the ion's progress and leaving it where it was. The measurement does not physically push the ion back. It does not add energy or remove energy. It simply forces the ion to declare its current state, and that declaration restarts the clock because the transition must build from the beginning again every time a definite answer is extracted. There is something almost tender about it if you let yourself feel it. A thing caught mid-change, repeatedly asked, "Are you still you?" And each time it answers, "Yes, it is." The asking keeps it where it is. The watching holds it still. This is not mysticism. It is the precise consequence of the quantum mechanical formalism applied to repeated projective measurement. The calculation makes a quantitative prediction, not just that the transition is slowed, but by exactly how much it is slowed as a function of the measurement interval. And the NIST experiment confirmed that prediction with beryllium ions in 1990. But there is a twist, and this is the part that even people who know about the quantum Zeno effect sometimes do not know, which makes it the quiet surprise hidden inside an already surprising story. The quantum Zeno effect is not the only thing measurements can do. In 2001, a team led by Mark Raisin at the University of Texas, along with colleagues Manuel Batista Gutierrez Medina and Meret Fisher, performed a related experiment with cold sodium atoms, and they found the anti-Zeno effect. It is exactly what it sounds like. Under certain conditions, specifically when the measurements come at a frequency that matches an intermediate timescale in the system's dynamics rather than either very fast or very slow, the repeated measurements can accelerate decay rather than suppress it. The system changes faster under observation than it would if left alone. This is not a contradiction of the Zeno effect. Both effects arise from the same underlying mathematics. The key is the relationship between the measurement interval and the shape of the system's energy spectrum, the range of frequencies at which the system naturally oscillates. If you interrupt a transition very rapidly, faster than the natural timescale of the transition's early quadratic growth period, you suppress it, Zeno style. If you interrupt it at an intermediate rate, tuned to a different feature of the spectrum, you can enhance it. The watching can freeze, the watching can also accelerate. What it does depends on how you watch. There is something in this that feels like a gentle warning about the metaphor of observation as passive attention. The quantum Zeno effect is sometimes described as a watched pot never boils, and the anti-Zeno effect would be, by extension, a pot that boils faster when you check on it too eagerly but not too often. As analogies go, both are useful for roughly one sentence before they start misleading you. What is happening is not about attention or anxiety or any humanly recognizable form of watchfulness. It is about the physical process of coupling a quantum system to a measurement apparatus in a way that extracts information about the system's current state, and the mathematical consequences of doing that at different rates. The word observation in quantum mechanics is a technical term. It means an interaction that produces a record, a physical record, somewhere in the environment of what state the system was in at that moment. It does not require eyes, it does not require a mind, it requires a physical record. When the NIST team fired measurement pulses at their beryllium ions, they were creating physical records. When Raisin's team performed their measurements on cold sodium atoms, they were creating physical records. The ion does not know it is being watched in any sense that would comfort an anxious mind. The ion's quantum state interacts with the measurement apparatus, and the result propagates into the physical environment, and that is what changes the subsequent dynamics. And yet, and this is worth sitting with gently in the dark, the effect is real. Measurement really does change what the system does next. The rate of measurement really does determine whether a quantum transition is frozen or accelerated. The physical world, at its smallest scales, does not evolve in isolation from the processes that extract information from it. Information is not a passive record of a world that would have been there anyway. Information is woven into the dynamics. That is the message of all 5 experiments, arriving at its clearest form here in the 4th. The double slit showed that which path information merely existing in the environment destroys interference. The quantum eraser showed that when that information is arranged to be inaccessible, correlations in the data reveal that interference was possible all along. Bell showed that the correlations between distant particles exceed what local hidden properties could produce, though no signal is sent. And the quantum Zeno effect, and its strange twin, the anti-Zeno effect, shows that the act of repeatedly extracting information from a quantum system determines the rate at which it changes, not observed in some vague poetic sense, measured precisely in a laboratory, with beryllium ions and sodium atoms and instruments and data and predictions confirmed to the degree of precision the equipment allowed. The world at its base is not indifferent to being measured. It is, in a specific and technical sense, partly constituted by the information that measurement makes available. That is not mysticism. It is the documented result of some of the most careful experiments ever performed. There is one experiment left, the fifth, and it is the one that sits most quietly among the five, less famous than the double-slit, less mathematically celebrated than Bell, but the one that in some ways requires the largest shift in how you think about what is physically real. Everything we have discussed tonight involved some form of contact. The electron was sent through slits and hit a detector. The photon's partner was measured or not measured. The entangled electron spins in Delft were inside diamonds but were nonetheless interacting with the local magnetic fields and measurement apparatus. The beryllium ion received pulses of light. The fifth experiment involves no contact at all. An electron was measurably affected by a magnetic field it never entered, in a region where every instrument available confirmed that the field was exactly zero everywhere the electron actually was. Nothing pushed it. Nothing touched it. And yet it changed. That is where we are going next. And so we arrive at the fourth movement, the one that has a name borrowed from a man who lived 2,500 years ago and who never thought, not once, about electrons or quantum mechanics or the decay of radioactive beryllium ions. He thought about arrows. Zeno of Elea was a Greek philosopher, a student of Parmenides, and he had a talent for constructing arguments that seemed obviously wrong and yet could not be immediately refuted. His most famous one went something like this. Consider an arrow in flight. At any single instant, any one frozen moment in time, the arrow occupies exactly one position in space. It is not moving. It is simply there at that location, filling that space, motionless at that snapshot. And since time is made of instants, and at each instant the arrow is motionless, how does it ever move at all? We know the arrow moves. We watch it move. And yet the argument has a strange, stubborn quality to it, a way of catching in the mind like a splinter. Mathematicians eventually dissolved Zeno's paradox with calculus, with the idea that an infinite sum of zero-length moments can still add up to a finite, traversable distance. That motion is not made of frozen snapshots, but is something continuous happening across intervals. The paradox was elegant and wrong, and it slipped quietly into the history of philosophy. But in 1977, two physicists named B. Misra and E. C. George Sudarshan were working on a very different kind of problem, and they found that Zeno's frozen arrow idea had, in the mathematics of quantum mechanics, a strange and literal echo. They were thinking about unstable quantum systems, about particles or atoms that are, left to themselves, going to decay, going to transition from one energy state to another, or to break apart and emit radiation. In the everyday world, these processes feel automatic and inevitable. A radioactive nucleus decays on its own schedule, obeying a half-life that seems built into it like a clock, ticking regardless of anything outside. Nobody has to look at it, nobody has to touch it. It just goes. But Misra and Sudarshan, working through the mathematics carefully, found something deeply strange. The mathematics of quantum decay, they showed, has a particular shape in its very early moments, right at the very beginning, right when the system has just been prepared, just set up in its unstable initial state. The probability of it having decayed does not grow linearly with time. It does not start at zero and immediately begin rising at a steady rate. Instead, it starts at zero and curves upward slowly. The curve is quadratic, parabolic, and for a brief window at the very beginning, the probability of decay is growing more slowly than intuition suggests. And this matters, they argued, in a remarkable way, because quantum measurement has a strange property. When you measure a quantum system, you don't just observe what it is doing, you reset it to a definite state. If you measure whether a system has decayed and find that it hasn't, you have collapsed it back to the undecayed state, you have reset the clock, you have put the arrow back in the bow. What this means, Misra and Sudarshan showed, is that if you measure frequently enough, if you keep checking whether the system has decayed, you can exploit that slow, early parabolic window over and over again. Each measurement that finds no decay resets the system to the start of that quadratic curve. Each reset puts the clock back to zero. And if you reset it often enough, the system never gets a chance to climb out of that slow, early phase into the steeper, exponential decay it would otherwise settle into. Measure often enough, they concluded, and you could suppress the decay almost entirely. The system, watched continuously enough, could not evolve. The quantum arrow, observed at every instant, could not move. They named this the quantum Zeno effect, because Zeno's philosophical joke, it turned out, had a real version, not for arrows in flight, but for unstable atoms under relentless observation. And then people went and tested it. There is a thing worth pausing on here, if you'll allow it. We are now 4 experiments into this journey. Each one has required a shift in what you take for granted about the physical world. The first required accepting that an electron, one single electron, fired alone, arrives as a wave of probability and only becomes a definite dot when something records it. The second required accepting that the correlations between distant particles are real and that the past cannot be simply rewritten, only differently illuminated. The third required accepting that local realism, the idea that the world has definite properties independent of measurement and that nothing influences anything faster than light, is not just uncertain, but experimentally dead. And now we are asked to accept that the act of observing, the mere act of repeatedly asking a system what state it is in, can suppress its natural evolution. If you are still awake for all of this, I want you to know that it is genuinely strange, and your sense that it is strange is correct. These things should feel surprising. They surprised the people who discovered them. They still surprise physicists. The strangeness is not a sign that something has gone wrong with the explanation. It is a sign that the experiment is real and the universe is like this. The test came in 1990. Wayne Itano, D.J. Heinzen, J.J. Bollinger, and David Wineland, working at the National Institute of Standards and Technology in Boulder, Colorado, the same NIST that would later be part of the loophole-free Bell tests, took a collection of beryllium ions and put them in conditions where they would, left undisturbed, transition between 2 energy levels over a predictable period of time. Transitions between energy levels in trapped ions were, by 1990, something NIST knew how to work with precisely. The group had tools of extraordinary delicacy. They could prepare an ion, let it evolve, and then measure where it ended up. They knew exactly what the natural undisturbed transition probability looked like, and then they started interrupting. They began applying brief pulses of light at regular intervals, quick measurements that asked, each time, whether the ion had made the transition yet. Not gentle observations, not casual glances, precise, technically demanding measurement pulses that reset the system to a definite state each time. They tried different numbers of pulses across the same total time interval: 4 pulses, 9 pulses, 16 pulses, 64 pulses. The prediction from Misra and Sudarshan said that more frequent pulses should suppress the transition more and more, pulling the survival probability up toward 1. And that is exactly what happened. At 4 pulses, the transition was partially suppressed. At 9, more so. At 64 pulses distributed across the same total interval, the survival probability climbed close to the theoretical maximum. The beryllium ions, interrogated fast enough, could not make the transition they would have made if left alone. The watched quantum pot, observed closely enough, did not boil. This is the result. This is the one worth holding. Not a metaphor. An actual measurement of a real physical system with real ions, real pulses, real data, confirming a prediction that seemed, when first made, to be on the surrealist edge of quantum mechanics. And the mechanism is not mysticism. The mechanism is this: a quantum system's decay is not a continuous, inexorable dripping, a steady and unchangeable flow. At the very earliest moments, it is slow. The probability curves up gradually before it steepens, and a measurement that finds no decay resets the system to that gentle, early curve. Do this often enough, and you keep the system perpetually in the slow, early window, never letting it climb into the exponential phase. The measurement is not magic. It is a physical intervention that exploits the shape of the decay curve. Now, here is the part I want you to sit with for a moment, because it is stranger still. We said that frequent measurement suppresses decay. More pulses, less transition. And this seems like it might be a general principle, a simple rule. Watch something quantum more and more carefully, and it will change less and less. Freeze it with observation. Zeno's paradox made real. But a group at the University of Texas at Austin found something that breaks even that simple story. Michael Fisher, Belen Gutierrez Medina, and Mark Raisin, working in 2001 with cold sodium atoms, found that if you tune the measurement rate differently, not too fast, not too slow, but at a specific intermediate rate, you can do the opposite. You can make the decay faster. You can accelerate a transition that would otherwise proceed at its natural pace. They called it the quantum anti-Zeno effect. The mechanism is subtle. It has to do with the energy distribution and the bandwidth of the final states available for the decay. There is a window in the measurement rate where the repeated interrogation effectively broadens the energy uncertainty of the initial state, connecting it more strongly to a wider range of final states and speeding the total transition rate. Push the measurement rate one way and you freeze the system. Push it the other way and you accelerate it. The same act, measuring, can do opposite things depending on how you do it. This means that watching something quantum is not simply neutral and not simply retarding. It is an active physical intervention whose effect depends on the specific coupling between the measurement and the system's natural dynamics. The observer does not collapse or freeze by virtue of being an observer. The measurement apparatus is a physical object with physical characteristics, a frequency, an energy, a coupling, and those characteristics determine whether the system slows or speeds. There is no magic here, there is physics. And the physics is, if anything, more interesting than the magic would be. Take a breath. There is one experiment left. The Zeno effect and its strange twin sit comfortably inside a certain frame. They are about measurement, about how often you ask a question. They are about the relationship between the act of knowing and the state of the thing known. And all the experiments we have walked through tonight have, in different ways, been about that relationship. The electron's pattern depends on which path information exists. The eraser's sorting depends on the coincidence of later knowledge. Bell's inequality is violated in a way that only becomes visible when you bring distant records together and compare them. The Zeno freezing is about how frequently you ask. In every case, there is a physical thing, an electron, a photon, an ion, and there is the structure of what can be known about it. And the relationship between those two things turns out to be deep, structural, not a peculiarity of quantum systems being small and fragile, but something woven into the mathematics at a fundamental level. But the fifth experiment sits apart from all of these in one particular way. All of the others involved some contact, some local interaction, some physical reaching in. Even if the conclusions challenge the idea of locality in a deep way, the experiment itself always featured some apparatus, some detector, some laser pulse physically present where the particle was. The fifth experiment involved no such thing. In the fifth experiment, an electron traveled through a region where every instrument available confirmed that the magnetic field was exactly zero. No force acted on it. Nothing was present at its location. And yet the electron changed. Its quantum phase shifted in a way that was measurably real and reproducible and predicted. And we are here. Akira Aharonov was a physicist from Tel Aviv, working in the late 1950s at the University of Bristol with David Bohm. Bohm, you may recognize, is the same physicist whose work on hidden variables had contributed to the theoretical framework that Bell would later examine and ultimately disprove in its local form. Aharonov was Bohm's student, young and deeply attentive to the foundational questions, the ones that standard physics education tends to package neatly and move past without quite answering. The question that caught Aharonov's attention was this: in classical electromagnetism, in the everyday physics of electricity and magnetism that Maxwell had formalized in the 19th century, there are two layers of mathematical description. There is the field itself. The magnetic field is a thing that exists at every point in space, pointing in a direction, having a magnitude, and it is the field that exerts the force. If you want to know what a charged particle will do in a magnetic field, you look at the field at the particle's location. The field is the physical thing. The force comes from the field. The field is real. Beneath the field in the mathematical structure, there is something else, something called the electromagnetic potential. It is a mathematical object from which the field can be derived. You take a certain mathematical operation on the potential, and out comes the field. The potential contains the field, encodes it, generates it. But in classical physics, this was considered a piece of bookkeeping, a convenience, a way of compressing the information about the field into a compact form that made calculations easier. The potential was not considered to be independently physical. What mattered was the field. The field was what pushed charged particles around. The potential was just a tool. In 1959, Aharonov and Bohm published a paper asking a question that this standard picture could not cleanly answer. What happens, they asked, to a charged particle that travels through a region where the field is exactly zero, but the potential is not zero? Because here is the geometry. Imagine a long coil of wire wound into a very tight cylinder, a solenoid. When current runs through it, a magnetic field builds up inside the coil. And if the coil is perfect, if the winding is dense and the geometry is right, the field outside the coil is essentially zero. All the field is trapped inside, but the electromagnetic potential, that mathematical bookkeeping object, extends outside the coil. It doesn't stay inside. It spreads out through the surrounding space, even though the field it corresponds to is tucked away in the interior. Now run an electron around the outside of this solenoid. The electron never goes inside. It travels only in the region where the field is zero. In classical physics, this means nothing happens to it. No field, no force, no effect. But Aharonov and Bohm worked through the quantum mathematics carefully, and they found something. In quantum mechanics, the electron is described not just by its trajectory, but by a wave a probability amplitude with a phase, and the phase they found was sensitive not to the field but to the potential. The potential, even though it did not manifest as a force, even though it produced no acceleration, even though the field at every point along the electron's path was exactly zero, still coupled to the electron's quantum phase. And if you split the electron, if you ran a beam splitter-style experiment where one path went around one side of the solenoid and the other path went around the other side, the two paths would accumulate different phases because the potential is different on the two sides, pointing in different directions, winding around the solenoid in different senses. When you brought the two paths back together, you would see an interference pattern. And when you changed the current in the solenoid, changed the enclosed magnetic flux, the interference pattern would shift, predictably, by a specific amount determined by the ratio of the enclosed flux to a fundamental quantum of magnetic flux. The electron would have been measurably affected by something it never touched, in a region where there was, by every field measurement, nothing at all. The potential, which everyone had agreed was a mathematical convenience, turned out to be physically real. Or rather, the field, which everyone had agreed was the physical thing, turned out not to tell the whole story. The potential carried information, the field did not. This was a very quiet bomb to drop on classical intuition. Chambers confirmed it the following year, in 1960. A first experimental demonstration showing the expected phase shift. The effect was real, but there were complications. It was difficult to be completely sure the solenoid was perfectly shielded, that no stray field leaked out to touch the electron's path. The critics had a point. The experiment needed to be cleaner. It took another 26 years. In 1986, Akira Tonomura, yes, the same Akira Tonomura at Hitachi, whose group had filmed the single electron buildup in the double-slit, whose name we met in the very first movement of tonight's journey, performed the experiment that closed the loophole. Not a solenoid this time, but something cleverer. A tiny toroidal magnet, a magnet in the shape of a ring, a donut, completely enclosed within a superconducting material. The superconductor is crucial. A superconductor expels magnetic fields from its interior by the Meissner effect, and when the toroidal magnet is fully encased in the superconducting shell, the field is confined inside with a completeness that a simple solenoid cannot achieve. The magnetic field outside the shielded magnet was, to the resolution of every available instrument, exactly zero. No stray leakage. And yet, when the electrons were sent around this shielded toroid, around the outside, through the field-free region, never penetrating the superconducting shell, never encountering any field, the interference pattern still shifted. Exactly as Aharonov-Bohm had predicted. The phase shift expressed in terms of the enclosed magnetic flux divided by the fundamental flux quantum matched. The loop was closed, the experiment was clean, the result was real. The electron had been changed by something it never touched, a force that did not exist at its location, a field that was zero everywhere it went. What this means, what it genuinely technically means, is that in quantum mechanics, the electromagnetic potential is not a mathematical convenience. It is a physical thing. It is locally real. It is what couples to the charged particle. The field, which in classical physics carries all the causal power, is in a sense a derived quantity, a projection, a shadow of the potential onto the local, force-visible world. But the potential underneath it is the structure that actually matters to the quantum phase. This is a deep shift. In the standard classical picture, a particle feels a force because a field pushes it where it is. The field is local. The force is local. Everything that affects a particle is present at the particle's location. This is one of the foundational intuitions of physics since Newton that causes our local, that the particle responds to what is here, not to what is somewhere else. The Aharonov-Bohm effect says, not quite. In quantum mechanics, the particle's phase responds to the potential, and the potential is not zero outside the solenoid even when the field is. The particle is sensitive to something global, something topological, something that describes the whole geometry of the situation, whether its path encircles the enclosed flux or not, rather than just the local conditions at each point along the path. And the word topological is worth a moment, because it is both technical and, once you see it, strange and beautiful. Topology is the branch of mathematics that asks about global shape rather than local detail. A sphere and a cube are topologically the same. You can continuously deform one into the other without cutting or tearing, but a sphere and a donut are topologically different. They have different hole structures, and no amount of smooth deformation converts one to the other. The donut has a hole that the sphere doesn't. The Aharonov-Bohm phase shift is topological in this sense. It doesn't depend on the exact path of the electron, how close it came to the solenoid, how fast it traveled, what shape it took. It depends on whether the path encircles the enclosed flux once or twice or not at all. It is counting holes. It is sensitive to the global topology of the situation. And this topological character turned out to foreshadow something enormous, a deep role of topological and geometric ideas in modern physics, in phenomena like the quantum Hall effect, in the geometric phase of Berry and others, in entire branches of condensed matter physics and mathematical physics that opened up in the decades following Aharonov and Bohm's paper. The quiet experiment with the shielded magnet and the electron phase shift was, in some ways, a door. On the other side of that door was a whole reorganization of how physicists think about what is real, what is local, what it means for a physical quantity to be present at a point versus present in a structure. And here is the thing I want to bring you back to, gently, now that we have walked through all five. We began tonight with a single electron fired alone across a dark room, hitting a phosphorescent screen. We watched, in our minds, the dot appear. One dot, alone and then another. And then, over hours and thousands of electrons, the pattern that no single classical dot could explain. The interference, the wave of probability collapsing to a point of fact, and the accumulation of those points revealing the underlying quantum shape of what was happening. We said the pattern vanished when the detector was active, not because a mind observed it, because information about the path existed in principle, in the environment, in the entanglement between the electron and the apparatus. Decoherence. The measurement did not require a conscious witness. It required an irreversible entanglement with something outside the electron. Then we watched as the eraser experiment showed that the correlations between particles carry a kind of latent structure, a division of the data into subsets that are always present in the results, waiting for the right sorting key. Not time travel, not rewriting the past, but something stranger in a quieter way. The universe does not commit to a single description until the information necessary to specify that description is available somewhere. The past that you see depends on what questions you have access to ask of it. Then Bell. Then the long experimental march from Clauser and Friedman in 1972 to the rooms in Delft and Vienna and Boulder in 2015 to the quasar light billions of years old used to set the detector choices. And the result, now clean enough to have earned a Nobel Prize, which is simply this. Local realism is false. The world does not have definite properties independent of measurement that only reveal themselves when you look. Or if it does, those properties are coordinated across arbitrary distances in a way that no signal could account for. You must give something up. The comfortable, solid, separate, pre-existing, definite world of everyday intuition does not survive. Then Zeno, then NIST, and the beryllium ions, and the measurement pulses, and the frozen transition, and the strange twin showing that measurement can accelerate just as well as it can freeze, depending on how you ask. And the deepest point there, the rate of change of a quantum system is not an independent, internal, untouchable property. It is bound up with the information environment, with how often the system's state is established by interaction with the outside world. And finally, the electron around the shielded magnet. No force, no field. A potential that the standard teaching called a bookkeeping tool, and a phase shift that proved it wasn't. What is the through line? What is the thing that all 5 experiments taken together are pointing at? They are pointing at this. The things we took to be solid and primary, position, trajectory, definite properties, local causes, the field as the real physical actor, turn out to be secondary. They are the effects, the visible shadows, the macroscopic projections of something more fundamental. And what is more fundamental, the thing that seems to actually organize quantum behavior, is information, potential, correlation, global structure, not what is here at this location at this moment, but what can in principle be known, what is correlated with what topology the situation has, whether the path encircles the flux or not. The popular version of quantum mechanics says the observer creates reality, consciousness collapses the wave function, the particle exists in all states until you look, and the looking brings one into being. And this is not quite wrong. It gestures towards something real. But it puts the emphasis in the wrong place. It makes the human mind the central actor in a drama that does not in fact require a human mind. The detector is not a brain. The eraser sorts data. It does not rewrite the past. Bell tests rule out a comfortable picture, but they don't prove consciousness governs matter. The accurate version is quieter, less flattering to human self-importance, and, I think, more beautiful. The experiments are not about consciousness, they are about information, about whether the information that would distinguish one possibility from another is available anywhere, in principle. When that information exists, the possibilities consolidate. When it is absent or erased, they remain superposed. The boundary between the classical and the quantum is not the boundary between observed and unobserved. It is the boundary between situations where which-way information is available and situations where it is not. And the Aharonov-Bohm effect adds one more layer to this. It shows that the relevant physical quantities, the ones that quantum particles actually respond to, are not necessarily the ones that look most real to classical intuition. The field is visible. You can measure it with a compass needle, with an electromagnetic probe. It deflects things, it curves paths, it does obvious, palpable work. The potential is abstract, gauge-dependent, defined only up to a mathematical freedom, and yet the quantum particle couples to the potential. The field is a consequence, the potential is the cause. Global structure, topology, is the thing that determines what happens, not just local force. This is not a failure of our experiments to find the real physics. This is the real physics telling us that its structure does not map neatly onto the structure of human intuition. Intuition was built for medium-sized objects at medium speeds in a world where information about position and momentum is always overwhelmingly available and always irreversible and always local. Intuition was built, in other words, for the limit in which quantum effects average out and disappear, in which decoherence has done its work so completely that the quantum substrate is invisible. We evolved to navigate that limit. We are exquisitely, beautifully calibrated for it. But the experiments do not live in that limit. They sit at the edges in the quiet places where individual particles move alone across carefully prepared dark chambers, where fields are switched in fractions of a second by random number generators, where diamonds in Delft and photon pairs from calcium atoms and sodium clouds, cooled to near absolute zero, are coaxed into situations that the everyday world is too warm and too entangled and too noisy to ever sustain. And in those quiet, cold, carefully controlled places, the structure underneath shows through. The rules were never broken, reality was always obeying its own laws, but the laws are not the ones intuition assumes. They are stranger. They are, in some ways, more intricate and more unified and more surprising than anything the classical picture suggested. And here is the thing about 5 experiments, about choosing to go slowly through 5 instead of racing across 100. You get to see the shape. You get to see the through line. Each experiment told in its own depth, with its own apparatus, and its own correction and its own honest mechanism, connects to the next. The double slit opens the question of information. The eraser refines it. Bell tests its outer limits across space. Zeno tests it in time. And the Aharonov-Bohm effect reveals it operating at a level we didn't even know to look for, in the potential rather than the field. That is not 5 separate weirdnesses. That is one deep structure approached from 5 different directions. And the structure has a name, not a single easy name, but the outlines of one. Quantum mechanics is the physics of information and correlation and global structure, not of locally definite objects and locally caused changes. We have come a long way tonight. I want to bring you back to where you are, back to your room, your lamp, your bed, the particular weight of whatever is covering you. You are, right now, a quantum system, not in a mystical sense, not in the sense of quantum energy, as used by people selling things, but in the precise technical sense that every atom in your body is subject to quantum mechanics, that the electrons in every one of those atoms are described by wave functions that would, if you could maintain coherence, produce interference patterns. The reason you do not see interference fringes when you walk through a doorway is not that you are special, or that quantum mechanics stops at some magical size threshold. It is decoherence. You are warm, you are complex. You interact with your environment, air molecules, photons, thermal vibrations, at a rate so overwhelming, so relentless, so total, that which way information about you is distributed into the environment before any interference can survive. The quantum reality underneath you is real. It simply decoheres so fast that the classical world we experience is the reliable residue. The same electrons that in Tonomura's experiment built an interference pattern 1 dot at a time, those electrons are in you. The same entanglement that in Delft violated Bell's inequality across 3 kilometers, that kind of entanglement is continuously forming and dissolving in the biochemistry of your cells, in the processes of your neural tissue, in the photoelectric responses of the proteins in your eyes, not maintained, not sustained in the way a laboratory experiment sustains it with extreme cold and careful isolation, but real for the brief moments it lasts before decoherence dissolves it back into the classical. You are not separate from these experiments. You are downstream of them. You are the macroscopic, thermalized, decoherence-saturated version of the same physics they are probing. The electron in the dark chamber and the electron in your atom are the same kind of thing, obeying the same equations, living inside the same fundamental structure. The experiments feel alien because they have stripped away everything that, in your daily experience, hides the quantum substrate from view. They are not showing you something foreign. They are showing you the floor beneath the house you live in. And somewhere in that is, I think, something settling. Not in a false or mystical way, not you are one with the universe as an invitation to stop thinking, but in the honest sense that the weirdness of these experiments is not weirdness that belongs to some other separate realm. It belongs to the realm you inhabit. The strangeness is native to where you are. You are made of matter that does this, that is like this, that obeys these rules. The phase that shifted around Tonomura's shielded magnet is the same kind of phase that describes the electrons in your body right now. The information-sensitive collapse that drives the double-slit result is the same quantum dynamics that operates in your molecular machinery. The universe is strange in a way that includes you. If you have followed all of this, all 5 experiments, all the corrections, all the careful, slow unfolding, then you have, in this long, quiet time, arrived somewhere that many people who have heard the word quantum have not arrived. You have the honest version, the one with names and dates and real apparatus and specific results. The one where the myths are named and set down gently, and the real thing is put in their place. You have Tonomura's single electron, one bright dot at a time, building the impossible pattern. You have Kim and Shih and Scully, and the coincidence counts. You have Bell's inequality violated in 3 simultaneous loophole-free experiments in a single year, confirmed with light from quasars that left their source before the Earth was formed. You have Etano and Wineland, and the beryllium ion that could not transition while it was being watched. And you have Aharonov-Bohm's shielded magnet, Tonomura's final confirmation, the electron phase shifted by a field that was everywhere the electron went, exactly 0. 5 experiments, 1 underlying shape. Before I let the night close around you, I want to say something about where this points. Not toward consciousness causes reality, not toward the simulation hypothesis, not toward any of the familiar philosophical extravagances that quantum mechanics tends to attract. Just toward this, the world is not built the way the senses suggest. The senses report a solid, local, definite, separable reality, and this report is reliable for navigating the scale of things where we evolved to navigate. But beneath that reliability, the structure is different. Information is load-bearing, correlation is real, topology matters. The electromagnetic potential is more fundamental than the force it generates. These are not mystical assertions. They are the verified, published, peer-reviewed conclusions of experiments you could, in principle, visit, replicate, examine. That is both humbling and, in a strange way, freeing. It means the everyday world, its textures and colors and weights and times, is an extraordinarily stable and coherent pattern that emerges from a substrate that operates by different rules. The pattern is not false, it is just not the whole story. And the 5 experiments we walk through tonight are 5 windows into the rest of the story, each one opened slowly and carefully so that what's on the other side is visible not as a blur of strangeness, but as a precise, lit, comprehensible scene. I am glad you were here for them. Wherever you are tonight, in whatever corner of the night, under whatever sky, I want you to know that we have walked a real distance together. From a single electron and a dark phosphorescent screen, through quantum erasers and entangled photons and diamonds in Delft, through beryllium ions frozen in mid-transition and electrons shifting around fields they never touched, we have covered the genuinely documented, genuinely strange, genuinely beautiful mechanics of reality at its smallest accessible scale. And if you are still here, thank you. If you drifted off somewhere in the Bell tests or let the Zeno effect carry you gently under, that is exactly as it should be. The ideas will still be here in the morning. You absorbed something, the shape of it is in there somewhere. If these slow journeys give you something, a sense of wonder, a quiet hour, a different way of seeing the ordinary world, then a like and a subscription to the Curious Voyager would mean more than I can easily say. Small creators like me rely on your support to keep these going. Every subscriber is another person choosing, on a given night, to let something careful and slow be the last thing their mind rests on. And wherever you are listening from tonight, whatever hour your clock reads, whatever the light is doing outside your window, I would love to know. Tell me in the comments where you are and what time it is in your corner of the world. The experiments are real, the results stand, and reality, strange as it turns out to be, is holding you in it without any effort on your part, operating its deep quantum mechanics at the scale of your cells and atoms and electrons, all of it thoroughly decohered, all of it thoroughly classical at the scale you move through, and all of it built on a foundation that 5 careful experiments have let us glimpse. Sleep well, fellow voyager. The next journey keeps until you wake.